Okay, good morning, afternoon, evening, Dr. Shafiq. I'm Vincent LOH, and this is my assignment one for digital VLSI design. Okay, this is the result and discussion part. Okay, so let's look at the assignment question. So they want us to from the state machine table here, they want us to obtain the ASM, flowchart, state diagram, and also so from here, um, this is my ASM. So the way I do it is, okay, so state 0 will be when the present state is 0, 0, and state 1 when present state is 0, 1. So this is state 0, state 1, state 3, 1, 1 is state 3, and then 1, 0 is state 2. Okay, so here 0, 0, 0, 1, 1, 0, then 1, 1, S3 is 1, 1. So the way I do it is I looked at, okay, so 0, 0 will go to 0, 1 no matter what. Whatever the input is, whatever RW is, whatever RDY is. So these are all these, don't care. So when the clock engage, if the previous state is S0, it will always go to S1. So my ASM here is, this one is CLK clock. So when you are at S0, whenever clock is engaged, it will always go to S1. That is the only criteria. Okay, same as over here lah. When clock is 1, it goes to S1. Okay, so when you're at S0, your output is 0, 0. When you're at S1, your output is also 0, 0. So no output yet. But once you're at once you're at S1, from S0 just now you come to S1, right? Okay, then your next state is now will be either 1, 1 or 1, 0. So from S1 you can either go to S3 or S2. So how do I differentiate this? I look at this 1, 1. It depends on RW. If RW is 0, it will go to S3. If RW is 1, it will go to S2. So my table. So when you're at S1, RW 0 equal to 0, RW equals to 0, right? It will go to S3. So RW equal to 0, it will go to S3. If RW equal to 1, it will go to S2. Let's look at once you're at, and whatever value is in RDY, it doesn't matter because that's the only thing. When RW change, the next state will change. Okay, so let's move on to S2. S2 is 1, 0. Okay, so these bottom 4. Okay, so when your possible next state is 1, 0, which is itself, and also 0, 0 with respect to S0. So how do you get 1, 0? It will look at, you can see, it now it doesn't look at RW, it looks at RDY. It looks at RDY. So if RDY is 0, right? If RDY is 0, it will stay at itself. It will stay in its own state. So S2 will remain S2. But if RDY is 1, it will go to state 0. So let's look at our ASM here. So S2, right? RDY 0, go back to itself. RDY 1, it will go back to S1. Okay. RDY 0, stay at S2. RDY 1, it will go to S0. Okay, then the last one also similar. So S3, 1, 1. So these 4, okay, S3, 1, 1. Also look at RDY. If RDY is 0, it will stay at itself. And if RDY is 1, it will go to S0. It doesn't matter what RW is. It only have to look at RD1. Okay, so it's the same. So S3, RDY 0, go back to S3. RDY equals to 1, it will go back to S0. Okay. So this is my ASM, and this is the state diagram. It's the same thing, same thing. Okay, let's move on to now K-map. So we can construct this K-map from looking at the table here. So my representation NS1 is Y1, NS0 is Y2, and then output OE and WE. I can circle the based on the criteria, and this is the output. NS1 equals to PS1 not PS or RDY not PS1. So all this, when we obtain all these four Boolean equation, we can then construct the functional block diagram. This functional block diagram follows this K-map. So example, OE is PS1 and PS1 not. PS1 here, PS1, PS1 not here. And then WE is PS1 and PS0. And the input NS1, NS0 is a little bit more complicated, but it's all just follow this K-map. Okay, right now we can move on to the Verilog. So to construct, constructing the Verilog to test the schema, this is what come up with. So input, yeah, this is the just to declare the input output. Okay, so input is clock, reset, RW and RDY, and our output that we want to measure, there is two, OE and WE, which is here, OE, WE, and I also want to measure the previous state and next state. And parameter, or here we declare S0, S1, S2, S3, so it's easier for us to refer when we write the next state logic. Okay, state register, this one always at positive edge, so this one is positive trigger, active high post edge clock and post edge reset. This means this one is a synchronous reset. Reset will overwrite the test bench. Okay, so if reset is true, then your present state will go back to S0 no matter what. Else if else means your clock is engaged, right? PS, your present state will be the next state will be your present state. So here the way I write my next state logic is similar to just now what I explained. So you can see I use case statement. Case, look at PS. So if PS is true, okay, in case we look at the PS. If it's S0, if your PS right now is S0, which is 0, 0, right? Present state is S0, it will begin, it will always go to S1. And this S1 is no criteria, because just now we see from the table there is no criteria, right? From the table, yep, no criteria, no matter what, it will always go to S1. Always go to S1. When you're in S1, if your RW equal to 0, you go to S3. If your RW equals to 1, you go to S2. The same as just now here. RW0, S3, RW1, S2. And then when you're at S2, RDY0, you stay. RDY1, you go to S0. RDY0, you stay. 1, you go back to S0. 1, you go back to S0. Same here, RDY. Oh, but the difference here between is the output for S1 is still 0, 0. S0 is still 0, 0. But for S2 is 1, 0, and S3 is 0, 1. And it's also the same. RDY0 stay 0, stay S3. RDY1 go to S0. Very simple, very simple. And then the test bench. Okay, this is the test bench. So we left hand side reg and reg clock reset RW RDY, and the output that we want to measure is wire OE WE. So this is initially we begin, we set everything as 0. Okay, the value here is just random, and this is the random value that I just key in. so that we can simulate all possible outcome from of the table. Okay, now we look at the simulation. So just now this one saying when we run, we will get when we simulate, we will get this. So at the beginning, this part doesn't matter because clock is still 0. Okay, so when clock becomes 1, so from here to here, right, your present state is 0. Okay, then it will go to 1 at the next clock cycle, which is here. Once this clock cycle engage, you will go to 1. Okay, so now when you're at 1, right, now your present state is at 1. 1, you will only look at RW, look, RW0 or RW1. Let's see. If this one, your RW is 0, right? Over here, your RW, from here to here, your RW is 0, you will be at 3. Your RW becomes 1 here to here. The next state is 2, and then here to here 0. Okay, that is state 1. Let's try and find state 2. State 2 here, it's a little bit more zoom in. Okay, so here state 2. So let's see, let's look at our here S2, right? S2, it will look at RDY 0 or RDY 1. So here our RDY is 1, which means it will go back to S0. Now here we go back to S0. Okay, then until here RDY becomes 0, S2, present state S2, RDY becomes 0, you will stay S2 long, and then this will continue. Let's see, this will continue. So you can see from here, RDY becomes 0, it stays 0, RDY becomes 1, it goes, RDY becomes 0, stay here, 1, go back. So you can see this one is 1, it will go back to state 0, this will repeat itself. The reason we get graph like this is because the random value that we key in, this is because so that we can simulate different outcomes. So we look at 0, we look at 1, see 0 always go to 1, 2, it will look at RDY. Let's look at 3. Okay, over here. Okay, over here. So before 3, let's see. 1, why does this present state 1 go to next state 3? It's because when you're at present state 1, if your RW is 0, you will always go to 3. You can see here RW is 0, nothing here, RW is 0. So all of this RW 0, okay, we go to 3. So now that we're at 3, S3 we will look at RDY now. RDY 1 you stay, RDY 1 you go to 0, 0, RDY 1 0, RDY 0 it goes to state 3, this one 1 0 0 state 3. So we have successfully simulated all possible outcome, and this is the before one more thing is we can open this. So with the schematic that we get, I think it come out like this is because of the FPG board that I choose. If I choose a different FPG board, it will maybe come up with a circuit that looks similar to mine, because it's basically the same. They just use a 2-to-1 multiplexer instead of the one that I use, which is a combination of N and OR gate. They both produce same result, as we can see from the just now from the graph that we produced. It's the same as the table, as the provided table here. The output we get. Oh, one more thing we forgot to look at is the output. See, the output when your present state is at 2, your OE is 1, no? Your present state is at 3, your WE is 1. This one, the output also matches. Okay, that is all. Thank you.